Hi guys, it's Kate. This week in section, we looked at first-order homogeneous differential equations and talked about qualitatively analyzing them, which was basically fancy for taking a look at a certain type of differential equation and being able to sketch pictures of what the various solution trajectories are. Most of the time, they look like this. We figure out what the important equilibrium solutions are for a particular differential equation. Then we take a look at the behavior of the various panels that the plane is now split up into. An equilibrium solution, where the solutions on either side of it are pulling towards that value, is known as a stable equilibrium, and one where one or both sides of the solutions are pulling away is an unstable equilibrium. Now, one of the interesting things is that this type of differential equation, this first-order homogeneous differential equation, is frequently used to model population growth. And what this is called is the logistic model. And when we're discussing this family of solutions right here, associated with a first-order homogeneous differential equation that is describing a change in population levels, we use some more appropriate terminology. First of all, what do these solutions generally look like? Well, there is almost always an equilibrium solution. Well, when you're dealing with population, there is always an equilibrium solution at zero, which basically means if the population level of a particular species is at zero, it's not going to increase or decrease from there. The number of the population is going to stay at zero, right? We're not actually making allowances for evolution. We're talking a short-term time here, and so that means that if you have 0 cats at t equals 0, then at t equals 1, you're still going to have 0 cats. They don't spontaneously appear. When you look at an equilibrium point like this, where above 3, the trajectories pull down towards 3, and below 3, they pull up to 3, this is the maximum number of whatever type of species you're talking about that your particular environment can sustain. And this is called a carrying capacity. Again, that's the level above which the population will shrink down to. Usually there are too few resources to sustain more animals than this. And then below which the animals will be able to reproduce and there are enough resources for the species to grow up till that level. Something else you may see in these qualitative solutions is something that looks like this. Note that there are 2 equilibrium levels that are above 0. Of course, there's an equilibrium at 0 because the population will not spontaneously begin increasing if there are no members of the species at a particular time. Note that up here we have a typical carrying capacity, a level for the species above which the level will decrease down to the carrying capacity, below which the level will increase up to the carrying capacity. But there's also this additional equilibrium level here. And this is called the minimum viable population. Basically, below this, there are too few animals to sustain the species, and so they die out. Above this, there are enough animals to sustain the species, and they'll increase through reproduction. So that's another piece of vocabulary that you'd like to know. So there are 2 major ideas when a first-order homogeneous differential equation like this is modeling population, right? First of all, you're definitely going to have an equilibrium level at 0. You're also going to have something that behaves like a carrying capacity, the maximum number of animals that the environment can sustain. And then you usually sometimes have a minimum viable population. So as you're working through some of your word problems, just know that these are the types of equilibrium levels that you will be seeing and working with. With what we've covered in class, you can pretty quickly put together what you'd expect to see in a differential equation that describes this. This one on the left would be described by the following. Here, the fact that there are factors p as well as 3 minus p are ensuring that there are equilibrium levels at 0 and 3. When we're dealing with population, we totally ignore what's happening below 0 because negative net values for population completely disappear. But in this particular case, this Kp is telling us about proportionate growth in between the 0 and 3 level. This 3 minus p is governing the equilibrium up here. And you can see the signs of the derivative appropriately match to what you're seeing in the sketches up here. So you can see where the carrying capacity shows up. Over here, this set of solutions is governed by something that looks like this. I gave this some arbitrary values for the equilibrium levels, but here you can see that P is creating the equilibrium level at 0. 3 minus P is giving us the carrying capacity equilibrium level, and then the P minus 1 term is giving us the minimum viable population equilibrium level. That's the level that below which the animals die out, and above which they grow and swell up to the carrying capacity. Note that I just include the K here because in general, the derivative is going to be proportionate to the population level. And that can be solved for once we learn how to solve explicitly for these. I hope this has been helpful for you to understand some of the word problems that you'll be working through. And this is an excellent application of the first order homogeneous differential equation analysis that we did in class. Enjoy your assignments, and of course, if you have any questions, don't hesitate to ask.